Welcome to the Ready Academy. Tools for teaching, tools for learning, tools for life. In this video book, we cover trigonometry. This content was produced with AI assistance and reviewed by a human instructor. We're starting with the story of trigonometry. Trigonometry did not appear all at once. It grew over more than 3,000 years across at least 4 civilizations, each contributing one essential piece. The story explains why we have the conventions we do, why 360 degrees, why the function is called sine, and why the modern unit circle definition arrived only in the 18th century. The history is also good company. This video book will return to its characters again and again. Why angles needed measuring. Long before anyone wrote down a trigonometric function, 2 ancient civilizations needed precise numerical control over slopes and arcs. The Egyptians needed to keep the face of a rising pyramid at a consistent slope from one course of stone to the next. The Babylonians needed to predict where the sun, moon, and planets would be in the sky tomorrow. The way each civilization solved its problem still shapes how we measure angles today. Egyptian master builders used a steepness measure called the seked, the horizontal run, in palms, per cubit of vertical rise. 1 royal cubit equaled 7 palms, so a sect of 5.5 palms per cubit produced the face angle used by the Great Pyramid of Giza, approximately 51.84 degrees. As a pyramid rose, course by course, each layer of stone was offset slightly inward. The seked told the mason exactly how far inward to step with every cubit gained in height. Trace a right triangle on the slant face. The vertical leg is 1 cubit, the horizontal leg is the seked of 5.5 palms, and the slope angle at the base is approximately 52 degrees. Problem 56 of the Rhind mathematical papyrus, copied by the scribe Ahmes around 1650 BCE, asks for the sect of a pyramid with a 360 cubit base and a 250 cubit height. The answer, 5 1/4 palms per cubit, is a cotangent ratio computed without any modern concept of an angle. The Egyptians could specify and reproduce a slope precisely, but they did not yet treat the angle itself as a measurable thing. The Babylonians took a different path entirely. Their place value numeral system used base 60, a number with 12 divisors that is astonishingly convenient for fractions. The Babylonian idealized calendar had 12 months of 30 days each, for a year of 360 days, one for each step the sun takes along the zodiac. Mapping 1 day to 1 degree of arc, a full circle divides naturally into 360 equal parts, 12 sectors of 30 degrees each. When Hipparchus of Nicaea applied this Babylonian arithmetic to all circles around 140 BCE, he fixed the 3-tier convention we still use: 360 degrees, 60 arc minutes per degree, and 60 arc seconds per arc minute. Figure 2. 2 ancient roots of trigonometry side by side. On the left, a cross-section of an Egyptian pyramid shows the seked ratio as a right triangle on the slant face, with the horizontal run labeled 5.5 palms and the vertical rise labeled 1 cubit. On the right, a Babylonian zodiac wheel divides a full circle into 12 30-degree sectors. The direct origin of our convention, that 1 full revolution equals 360 degrees. Every protractor, every clock face, and every map of latitude and longitude descends from a Babylonian count by 60s. The Egyptians measured slope as a ratio, run per rise. The Babylonians measured position as an angle, degrees around a circle. Which approach is more useful for a builder? Which is more useful for an astronomer? What does each approach take for granted that the other does not? From chords to half-chords. The next conceptual leap was the realization that an angle has measurable consequences, that the position of a point on a circle is a function of how far around the circle you have traveled. Once that function is understood, you can tabulate it once and reuse it forever. This insight, more than any other, made trigonometry an independent mathematical subject. Hipparchus of Nicaea, working in the 2nd century BCE, is the earliest mathematician known to have compiled a table of chords. For a given central angle in a circle of fixed radius, the chord is the straight line segment joining the two ends of the arc. Hipparchus tabulated chord lengths in 7.5-degree increments, using a circle of radius 3,438, chosen so that the full circumference would equal the 21,600 arc minutes in a 360-degree circle. Figure 3. A circle of fixed radius with chords drawn for 5 central angles: 30, 60, 90, 120, and 150 degrees, each chord labeled with its length as a multiple of the radius. As the central angle grows from 0 toward 180 degrees, the chord grows continuously from 0 toward the full diameter, and this systematic relationship between angle and chord length is exactly what Hipparchus chose to tabulate. 3 centuries later, Claudius Ptolemy of Alexandria refined Hipparchus's table to half-degree increments in the Almagest, and proved a theorem about cyclic quadrilaterals that yields, in modern language, the sum and difference identities for sine and cosine. The decisive simplification came not in the Mediterranean but in India. The astronomer Aryabhata, writing the Aryabhatiya in 499 CE, realized that working with the full chord of an arc is awkward, but working with half the chord is clean. The half-chord is the perpendicular dropped from the midpoint of the chord down to the center of the circle, and it is the modern sine. Figure 4. 3 views of the same arc side by side. On the left, a Greek chord stretches straight from one end of the arc to the other. In the center, Aryabhata's Jaya drops a perpendicular from the midpoint of the chord toward the center, producing the half-chord. On the right, the modern unit circle picture reveals that this half-chord is exactly sine theta, the y-coordinate of the point on the unit circle at angle theta. Aryabhata called his half-chord Jaya, the Sanskrit word for bowstring, because a chord taut across an arc looks like the string of a drawn bow. The word sine arrived in Latin Europe by a route that mathematicians still tell each other for amusement. The word sine traveled from Sanskrit to English through a chain of 4 translations across 700 years. Sanskrit Jia was transliterated into Arabic as jiba. Since Arabic script omits short vowels, jiba was written as the bare consonant cluster JB. Later, Arabic readers encountered the unvocalized JB and read it as jaib, a real Arabic word meaning bay, cove, or the fold of a garment. When Gherardo of Cremona rendered Arabic mathematical texts into Latin around 1150 CE, he translated jaib as sinus, Latin for bay or fold, and from sinus comes the English sine. The most fundamental function in trigonometry is named after a body of water because a 12th century translator faithfully translated a 9th century misreading of a 5th century Sanskrit word for a bowstring. Cosine arrived as the complementi sinus, the sine of the complementary angle, which is why the prefix co appears in cosine, cosecant, and cotangent. If Aryabhata's half-chord is the same idea as the modern sine, why do you think it took European mathematics roughly 1,000 more years to adopt it? What might be missing if you only have a table of chords and not a table of sines? Trigonometry becomes its own subject. The final stage of the story is the emergence of trigonometry as a self-contained discipline, separate from astronomy. This happened gradually across the Islamic Golden Age, the Indian Kerala school, and the European Renaissance, and was sealed by a single 18th century book. In the Islamic world, Muhammad al-Batani compiled sine tables around 900 CE that replaced Ptolemy's chord tables entirely. Abu al-Wafa al-Buzjani, working in the late 10th century, defined and tabulated all 6 trigonometric functions: sine, cosine, tangent, cotangent, secant, and cosecant, and proved the sine addition theorem in essentially its modern form. Nasir al-Din al-Tusi, writing in 13th century Persia, gave the first systematic treatment of trigonometry as a subject entirely separate from astronomy, stating and proving the plain law of sines and classifying the cases of spherical triangles. By the time al-Tusi was finished, trigonometry was no longer a toolkit appended to astronomy. It was a discipline in its own right. Meanwhile, in 14th and 15th century India, Madhava of Sangamagrama and the Kerala school did something extraordinary. They discovered infinite series for the sine, the cosine, and the inverse tangent. These are the very series that Isaac Newton, James Gregory, and Gottfried Leibniz would rediscover in Europe 3 centuries later. You will meet them later in this video book. Europe entered the conversation in the 1460s, when Johannes Müller of Königsberg, known as Regiomontanus, wrote De Triangulis Omnimodis, meaning on triangles of all kinds. The first European book to present trigonometry as a standalone mathematical subject. In 1595, the German mathematician Bartholomaeus Pitiscus published a short Latin treatise titled Trigonometria, the first time the word trigonometry appeared in print. And in 1748, the Swiss mathematician Leonhard Euler published the Introductio in Analysin Infinitorum, which redefined sine and cosine as functions of a real number rather than as line segments in a circle of arbitrary radius. Euler fixed the circle's radius at 1 once and for all, established the radian as the default unit, introduced the notation sine of x and cosine of x, and proved the formula linking trigonometry to exponentials and complex numbers. The unit circle, the radian as default, and Euler's formula tying trigonometry to the exponential function all became standard in this one book. Figure 5. A timeline of trigonometry across 4 millennia, from the Babylonian tablet Plimpton 322 around 1800 BCE to the digital age. The markers from left to right span Egyptian slope measurement, Greek chord tables, Indian half-chords and infinite series, Islamic sine tables and the 6-function system, European Renaissance treatises, and Euler's unifying Introductio of 1748. Each civilization added an essential piece, often unaware of what others had already done. The modern subject is their collective creation. Trigonometry is sometimes presented as a Greek invention. The historical record shows it as a deeply multicultural enterprise. Egyptian, Babylonian, Greek, Indian, Persian, Arab, and European mathematicians each added an essential piece, often unaware of one another's work. Why might this matter for how the subject is taught? Does knowing where an idea came from change how you understand it? That wraps up the story of trigonometry. Next up, Section 2, Angles and how we measure them. If you found this helpful, like and subscribe and support the channel